Case 6.6 has no calculus. It's a review of exponentials and logarithmic functions. Definition goes, if a is bigger than 0 and a not equal to 1, then the log base a of x equal y means that x equals a to the y. This definition is extremely important, something that is going to keep on coming up back and forth. We normally memorize this definition and go from it. I found a better way of really applying this. So just keep in mind the base of the log cannot be a negative number and it can't be a 1. Same thing with the base of an exponential function. So this is exponential and this is logarithmic. Now there are 3 properties of logs. The log base a of 1 is always 0, no matter what the base is. Log base 3 of 1 is 0, log base 15 of 1 is 0, log base a half of 1 is 0. Also, if you take a log, this right here is an English word for a piece of wood. For you to talk about a log, you must give it a base and you must give it an argument. You must take the log of a quantity. It can't be just the log, just like sine. You can't just say that's not sine. To be a sine function, you must give it an argument or an angle, right? Otherwise that will be a sin. So, if what you're taking the log of happen to be an exponential, in which the base of the log and the base of the exponential match, they undo each other. We're going to use that to our advantage. Also, if you're looking at an exponential function is when you have a number raised to a variable. So if you have an exponential function in which the power, the exponent of the exponential happens to be a log, in which the base of that log and the base of the exponential match, those also undo each other. Students like to cross them out this way, whatever works. So to really go back and forth, example 1 and 2 are extremely important. That's really applying the definition, but we're going to apply the definition by using properties. So when I see an exponential and I'm trying to get rid of it, I would log both sides. It says, write each of the following expressions in logarithmic form. The way it works, if I have an exponential and I can't seem to get around it, what I do, I would log both sides. Now, what base should I use so that the exponential will disappear? Well, for the exponential to disappear, I need a log with the same base. So if I make this the base of 5, remember, whatever you apply the log on the left-hand side, you must apply it on the right-hand side. And it has to be the whole side. So on the left, those undo each other. I'm left with a negative 3 equals log base 5 of 1 divided by 125. So the first 2 examples are nothing more than you going back and forth between those 2 forms of the definition. It's not gonna appear as if you're not sure why you're doing that. That's coming up in the remaining of the section and the remaining of the course. Again, if I look, this is the exponential. To get rid of the exponential, what I'm going to do, I'm going to log both sides. What base should I use to eliminate the exponential? Well, whatever the base of the exponential is, I should match. And whatever this base is, this must be as well. That's the condition for you to log, kind of like squaring both sides of the equation or square rooting both sides of the equation. You could log both sides of the equation, but you must choose the same base to do so. So that's 1/2 equals log base 16 of 4. In case you're wondering, what does a log find? It's kind of hard to remember, but I'm going to tell you what it is. A log asks, when you look at a log, it's asking what power do you raise the base to get the argument. So something like log base 5 of 25, for example. Log is finding what power do I raise the base to get 25? In that case, that will be a 2. Again, that's coming up later on. For now, just bear with me. Apply this definition back and forth. To get rid of the exponential, again, make sure you see the exponential. Take the log of both sides. What base should I use? A base 7. Those two will undo each other, and I'm left with a log base 7 of 1/4/49. Now, in case you don't remember, log is the inverse of the exponential, and the exponential is the inverse of the log. The second set of problems, what we want to do, we want to write these expressions in exponential forms, even though there's an equal there. Maybe I should change that to equations. Well, it doesn't matter. So I should say, not expressions, I should say equations. There we go. Okay, so if I want to change the following equations to logarithmic form, here I have a log. Guess what? I'm going to use the third. And I know you're not used to this, but once you do this enough, you'll start working this in your head. You start jumping from this to this without writing anything. Here, what I want to get rid of log. To make use of that, I'm going to make each side, and be careful, it has to be the whole side. I have to make this whole side a power of an exponential. As long as I make this a power of an exponential, that will work. What base should I use to eliminate a log? Again, you look at the base of the log and you proceed. You should make that a power of the base 2, and those two will undo each other by property 3, and 32 will equal 2 to the 5th. And that's pretty much it. Just want to run back and forth, nothing more. I go to the next problem. I notice the base is 1/3, so the same deal. I'm going to make the whole left side a power and the whole right side a power of 1/3. And that will work as long as you satisfy this condition. So those will undo each other, and I'll get 27 equal 1/3 to the 3rd power. And I'll point that out as we do more examples and applications. And here again, the base is a 7, so obviously I need to make this a power of an exponential with a base of 7, and those undo each other, and 1/49 equal 7 to the -2. Now the graphs of those, I'm hoping you remember those. I'm going to remind you really quick how this works. If you want to sketch a graph, if you recall exponential growth or exponential decay, if the base is bigger than 1, so look at the definition. It says right there, that's an exponential. A is bigger than 0. And not equal to 1. So there are two conditions for A. Either A is between 0 and 1, or A is bigger than 1. If A is bigger than 1, let x equal 0, y would be 1. That's a point that's on all the graphs of exponentials that are not shifted. And the graph really looks like this. I'll elaborate on that more in class. You have 3 things to worry about. 1, there's an asymptote of y equals 0. You can never get to that. You could choose the value of x to be as small as you like. Y would be as close to 0 as you like, but never 0. And if the base is bigger than 1, that's exponential growth. 3 things you need: the asymptote, that point 1, 0, and the shape of the graph. If I multiply the x by a negative, that will reflect the graph with respect to the y-axis. So take this graph right here and flip-flop it with respect to the y-axis, and the graph will be identical to what it did, except it'll switch. if I look at the graph of part C, I'll notice that the base is between 0 and 1, so that's exponential decay. Again, this book only has 3 examples. I'd like to do more, but the graphs don't come up as much. And since log is the inverse of an exponential, what do you know? A graph and its inverse are symmetric with respect to the line y equal x, or since this is the inverse of 2 to the x, you switch x with y, the point 1, 0 becomes, the point, oh look at that, what do you know? The point 0, 1 becomes 1, 0, and y equals 0, if you switch x with y, become x equals 0, and if you reflect this graph with respect to the line y equal x, you will get this graph. Now, we have 3 laws of logs. The log base A of m times n. Here we're assuming that m is bigger than 0 and n is bigger than 0, and all of the theory assuming it applies. If you multiply 2 logs, keep in mind, if I multiply exponentials, don't you add the powers? When I take log base A of the product, that becomes the sum. I could derive those for you, but that's not the purpose here. I'm supposed to be reminding you of this. Here, when you divide, when you take the log of 2 things divided, that's like a to the x divided by a to the y. If you're dividing, don't you subtract the powers? And that's where the minus comes from. And here, if you raise, if you take the log base a, so if you take a to the x raised to the n, don't you multiply these powers? You end up moving up front and multiplying it, and that's a property that no other function has so far. So we're going to practice this a bit. The catch to go from right to left and left to right, that has to be a 1 for me to combine 2 logs. So I see there's a 1 there and a 1 there. I'm in good shape. 2 logs with a plus in between. If I want to go back, I could write that as a single log of base 2 of 5 times 3. So that would be the log base 2 of 15. And if I see 2 logs with a minus, as long as that's a 1 and that's a 1, I could combine those into a single log of whatever the first is. And the minus, I always think of it as a division of whatever that is. The order is very important. You can't switch those. It has to be the 2 over 7. You can't write 7 over 2. I get to the last example, the third example, C, and I notice, wait a minute, that's not a 1. I use the third law. I use it in reverse to go that way. So I move that and make it a power of the argument. That becomes the log base b of z to the 4th minus the log base b of z to the 5th. Here there is a 1. I don't have to worry about that. So that is a single log base b of, and I divide again, z to the 4th over z to the 5th. And for now, we simplify, of course. For now, we're going to leave the answer like this. Later on, we simplify it further. That's 1 over z, and there's my answer. There are 2 ways to every problem. We're looking at this from one direction. If I had 3 logs, now in the beginning you could really take your time and say, okay, you know what, that's a 3, I know what needs to be done. That's a half, I know what needs to be done. And that's a 2, I know what needs to be done. I'm going to use the third law to reverse the order. And I could do this a step at a time. I'm going to show you that. So you could say that is the log base 7 of, and you could start with those two first and say, well, that's going to be y cubed. There we go. That's going to be y cubed divided by, isn't that the square root of 4? And that's going to be the log base 7 of whatever this is, y cubed. Square root of 4 is 2 times 25. And my final answer would be the log base 7 of 25 y cubed divided by 2. Now, what's the alternative? The alternative is for me to take a shortcut. So, you know what? I know this is going to be the log base b of x to the 5th plus the log base b of a to the 1/4 minus the log base b of 2 to the 3rd. And the shortcut is for you to write a single log one shot, the same base, and this is how it works. All the additions will be multiplied at the top, and all the minuses will be in the bottom. So x to the 5th plus, you multiply by the 4th root of a, and since that's a minus, I put that in the denominator, save myself a couple of steps. And 2 to the 3rd is actually 8. And I'm done.